Yeah, cams on you. Let's start off. The last thing that we did was your stable and unstable equilibrium. Okay, so let's see a question based on this. Are the cams on?
Volume.
So let's say we have a graph like this. We have an fx graph. We have a ux graph. We have 3 points here. So this is A, this is B, this is C, this is A, this is B, this is C. Which point is stable equilibrium and which point is unstable equilibrium? So first one is a force x graph, and second thing, use your potential energy. Let's get this. How do we approach this? Cams on everyone. Again, remember the conditions. What is, first of all, what is equilibrium? Force must be 0. What is stable equilibrium? If you displace from there, it should come back. Or potential energy is minimum. Unstable equilibrium, potential energy is maximum. How do we try this? Think. Take a minute, then I'll show you. This 14th A, na, first part which was came, this was a mains ka PYQ. It's a standard question. Okay, let's see. Let's see the first one. Now, I'll show you one completely mathematically, and then I'll show you more intuitive also. Now look at the point here. So at A and C, force is 0. B mein force is not 0. So B is nothing actually. For equilibrium, F must be 0. So force at A and force at C is 0. Force at B is not 0. Look at this thing. So at A and C, the force ka value is 0. So B is nothing. B is not stable equilibrium. B is not unstable. It is not equilibrium only. Now we will see mathematically for stable. the potential energy is minimum. Means the double differential d square u by dx square must be greater than 0. But we also know force F is nothing but du by dx. So this can be written as d by dx of du by dx. This can be written as greater than 0. If you multiply minus sign on both the sides, we get df by dx is less than 0. That means in an fx graph, if the slope is negative, it's a stable equilibrium. Two conditions should be satisfied. One, force must be 0, and then the slope must be negative. So in slope in fx graph is negative. It's a stable equilibrium. So where is the slope negative? If you look at A here, A slope is positive. At point C, the slope is negative. Like I said, this is completely mathematical. So therefore, C is stable. Making sense? Similarly, for unstable, I can use the same logic. For unstable, U is maximum. So d square U by dx square must be less than 0. This will become d minus df by dfx is less than 0. So df by dx must be greater than 0. Positive slope. Therefore, A is unstable. That means if you put a particle at A, it will move off, and if you put it at B, it will just come back. Remember this is not the path of the particle. This is the graph. That means, you know, how will the path should have been? Again, we are just guessing. The path should have been something like this. So for this guy, the path, if you try to draw, so A is an unstable. So at point A, there is a peak. B is some random point in the middle. C must be a valley. You're getting? This must be the path. I hope you're making sense.
So it can be 1D2, right?
It can be.
One-dimensional also.
This is one dimensional only, fx graph. What do you mean by one dimensional also? Matlab?
सर मतलब वो मोशन इन अ प्लेन है ना जो
This is fx record.
सर नहीं जो
There is
आपने
plane
पाथ
means x
बनाया
and
है
y. So this is just a height na, with y and x ka height. Yeah. I'm just saying roughly it looks like that.
ओके
Just an example. I know you can create different paths. I'm just giving one example how it could have looked. Na? What you're saying?
यस सर सर आई मीन
See,
the slope part which you said was kind of relating to
for a
the d square y by dx square for the potential energy graph.
huh. In that thing, it will be a yx graph. Yeah.
हाँ तो that will shows minima and maxima.
हाँ वही है. Everyone got this? How to do this mathematically? Now there is a more intuitive way to do this thing. So listen carefully. By chance, exam doesn't click all the differentiation stuff. Look at point A. So when you're at A, now if you push the particle little forward, see what happens. So at point A, if displaced forward, means if you push it little forward, then look at the force here. F is positive. Means can you see? If you go little forward, the force is also forward. So what will happen? Will you come back? You'll keep going forward only, right? If I push you forward and you're also going forward, why will you come back? You'll keep going forward. So if displaced forward, force is also forward. Similarly, if you push it backward, the force is also negative. Means if I push you forward, you'll keep going forward. If I push you backward, you'll keep going backward. What kind of point is this? Stable or unstable? Unstable, isn't it? Because what is stable? If I push forward, it should come back. If I push backward, it should come front. Right? If displaced backward, the force is also backward. Again, this is just an intuitive thing. So means it does not come back. Therefore, this is, so it doesn't come back. So such a point is unstable equilibrium. But look at C. If I push forward, the force is negative. Means if I push forward, force is pulling you back. If I push you backward, the force is positive. If I push you backward, force is pushing you forward. So this is stable. Is this logic making sense? So that is a easier way to interpret it, stable and unstable, if you don't want to use a mathematical part. Any doubts on this? All clear with this? Still, there's one more question here. What about the B part? What if this graph? It's a UX graph. This is easy. Remember, whenever someone says equilibrium, the first thing you need to find force is 0. F is equal to minus du by dx. That means in a UX graph, you need the slope to be 0. At B, du by dx is 0. Therefore, force is 0. At A and C, force is not 0. So A and are nothing. Here, A and C are not equilibrium, unstable equilibrium. And look at C. You can clearly see at B, potential energy is also maximum. So you tell me, if the force is 0 and potential energy is maximum, what is B? Therefore, B is unstable. So be careful what kind of graph is being asked. If it is an fx graph, B is useless. If it is a UX graph, A and C are useless. All clear with this? Any doubts on this? Siddesh, clear? Yashvi, Tanishka, clear Yashvi? Shaurya, Pratyasha, Anvita, Advait, clear with this? Great. So that's a bit about stable and unstable equilibriums, but we will see these kind of questions, right, will pop up more in other chapters, but the idea is important.
Sir,
Next thing.
sir, how at B is du by dx equals to 0?
What is du by dx? Say something. No? What is du by dx? Slope.
Yes, sir.
So what is slope?
Oh,
0. It's a flat line. Yeah.
Sir, can you please take like a case for me? I want to like understand something from them. Sir, I have like a double like a
Can you
feeling
ask after the
between.
end of the class?
Okay,
That would
sir.
be better, right? Why do you want
Yes.
to just poke in the middle of this thing and mess up for everyone else? So let's see. You have a question, you have to send me the question. You're getting it?
So like
कुछ
it's
है
not
ऐसा
a
question?
question. It's not a question. It's just
Then class के बाद पूछो
doubt.
ना. हाँ देखते हैं ना class के बाद. When did I say no for your doubts? Class का बीच में. Next one, see. So gravitational potential energy. So till now we discussed about potential energy, but that is more general. Okay, so you can have potential energy different types. We'll call this thing GP. So let's say if you take a block of mass m, and let's say it is going in some random path. Let's say this height is HA, this height is HP. So as this block is going, at every instant, if you look at the force is always mg acting downward. So what is the work done by gravity? Work done by gravity is minus the force, minus mg j cap, dot the displacement, hb minus ha j cap. Therefore, the work done will be minus mg into hb minus ha. Since force is constant, I can directly use f bar dot s bar. And from the definition of potential energy, what is work done by internal conservative forces? Work done by internal conservative forces is negative of potential energy. Again, the derivation is not really that important, but the idea that delta u minus goes off, we get delta u is equal to mg delta h. This is what you studied in school. The change in potential energy is simply mg into change in height. And if you observe here, the potential energy does not depend on the path, it only depends on a particular position. Now, if you choose something as reference, now this is important. Whenever you say potential energy at a point is so and so, we need to always define a reference, because it's like this thing, tell me one thing, is this line big or small? On a paper, if I draw a line, is this line big or small? It depends, right? If I draw a smaller line, it is big. If I draw a bigger one, it is small. So the thing is, you need to always have a comparison. You just can't say it is big or small. So same way, when you say potential energy, you always need a reference line. So if you take A as a reference, you can choose anything as reference. That is, you're taking the height at A as a ground level. Then the potential energy at A is 0. Then your formula becomes U is equal to mgh, where h is the height from the reference. This is what we studied in school. Let's talk about a little more about this. Is the idea clear what we did? We found work done by gravity, and then we said whatever work you're doing, that will be negative of potential energy. Now listen to this carefully. Suppose if I take a situation like this, an incline, and let's say we have a block of mass m here at the top, and the height is h. Now if I ask you this question, what is the potential energy? What will you say? If a block is at a height h, what is the potential energy? If I just ask you this question, now there is a problem. You need to ask yourself, boss, what is your reference? Suppose if you choose the ground level as reference, or if you choose this level as reference, or you can even choose this as a reference, where this is also height h. Now see, the answer changes. So if you ask me what is the potential energy of the block, so the question is who is asking. If you say reference 1, then the answer is mgh. If you say reference 2, then the answer is 0. If you say reference 3, it is below the level minus mgh. Can you see what is happening? potential energy depends on who is the reference. Clear with this? So you just can't assume it as a ground. Generally, yeah, we assume the ground as a reference, but that is the case. Suppose if the block has reached the ground level, suppose if this block is at ground, that means if the block reached the ground. Now, if you ask the potential energy, then reference 1 will say 0. Reference 2 will say mgh. Minus mgh. Reference 3 will say minus 2 mgh. Interestingly, one thing, if you take the difference, if you take the U block minus the U ground, look at the difference. mgh minus 0, mgh. 0 minus mgh, mgh. Minus mgh minus 2 mgh, mgh. Did you see something? So the difference in potential energy, so when the block goes from here to here, the difference in energy is always mgh, independent of reference. So this will be a theoretical question like this. Potential energy difference is independent of the reference line. It doesn't matter where you stand and see, the difference will be always same. Whereas potential energy depends on the reference. Potential energy difference is independent of reference. Yeah, it kind of feels obvious, but exam when they give this question, people get mixed up with both the statements. If you just say potential energy, it depends on the reference. So just be careful with this, more of a theoretical thing. So if I had to give an analogy, think of like this. Imagine you have a centimeter scale. And there are divisions like this. Okay, so it's a centimeter scale, so each division is 1 mm. What is the difference between these two divisions? 1 centimeter, right? The difference between these two divisions is 1 centimeter in a centimeter scale. Now, if I say this is 16, then what is this number? 17. If I say this is number 3, what is this number? 4. If I say this is 11, then this is 12. Can you see something? The digit will keep changing based on what is this, but the difference will always remain same. Are you getting what I'm trying to say?
Yes, sir.
So on a scale, what is the division will depend on what is the previous division, but the difference will always remain same. So something of that sort. When you ask potential energy of a block, it depends on the reference line. If I ask you potential energy difference, it doesn't depend on the reference. Clear with this? So anyway, what is gravitational potential energy? mgh, where h is the height from reference. Let's keep it simple. Any doubts on this? Yeah. Next thing, spring potential energy. Then now we're defining all potential energies. We'll call this thing SPE. So if you got a spring, this is your natural length. K is your spring constant. So if the spring is being pulled outside by X, we know the spring force will be pulling inside. And remember here, the force is not constant. The more you stretch the spring, the more force you get. So the work done by spring force will be integral. The force is backward, whereas the displacement is forward. You get a minus FTX. So when it goes from 0 to X, this work done will be minus half kx square. So spring does this much work on the person who is pulling it. And the work done by spring force is equal to minus delta U. So from here we get minus half kx square is equal to minus delta U. So here we get the spring potential energy is given by half kx square. So whenever you stretch the spring by x, the energy stored is half kx square. The reference line is the natural length. That is important. Always you have to define your reference line. So whenever you stretch a spring by x, the force is kx, but the energy stored is half kx square. Here x is elongation or compression from natural length. So it doesn't matter whether you elongate or compress, the energy is same. This is your second one. There, that's your second formula, everyone. So there, till now we know two energies. One is your gravitational potential energy, mgh. One is the spring potential energy, half kx square. Any doubts on this? All clear with this? The third one is your kinetic energy. Again, this is straightforward. So if you take a block M, let's say it is going with some speed u, and let's say there are two people here. Let's say we have an observer A here at rest, and let's say we have an observer B who is going with speed v. So if you ask the kinetic energy, A will say the kinetic energy of A is half mu square. But if you ask B, what is the kinetic energy? B will say the kinetic energy is half m u minus v whole square. So kinetic energy depends on the frame of reference. Depending on who is seeing it, kinetic energy varies. There, these are the three energies we are going to play around with. Clear with this? Any doubt so far? Let's see a question. Then we'll go ahead. Let's say you have taken a non-standard spring. Your standard spring is F is equal to kx. So you have constructed a weird spring where the force F is given by minus kx cube, where x is the elongation or compression from natural length. So W1 is the work done by external force to stretch from x is equal to x0 to 2x0. W2 is the work done by the external force to stretch from 2x0 to 3x0. You're getting? So this weird spring, you took it and you started stretching it. When you stretch the spring from x0 to 2x0, you have to do some work. When you stretch it from 2x0 to 3x0, you have to do some work. That is W1 and W2. Find the ratio of W1 by W2. Again, it's more of a work question. Is the question clear, everyone? You have created a weird spring where the force is minus kx cube. It's not a linear function. X is either compression or elongation. So when this spring you're pulling from x0 to 2x0, you must have done some work. When you pull from 2x0 to 3x0, you must have done some work. What is the ratio of these two works? Let's get this.
So the natural length is x naught, right?
No, natural length will be 0. This is elongation, right?
Okay, okay.
Right, Samya? X naught is the elongation. The elongation has gone from x naught to 2x naught. We have one answer. Others try trying out a minute. Just give it a try and get some water and come. Let's see. Yeah, a few more answers. Right, Arya. Right, Ishman. नहीं उत्साह. Siddesh, I think you got reverse. Anshika, right. Ovia, right. Yeah, most of you got it. Let's see. So here's the work done. So when you take the spring here, so the F external is pulling out, and this is your X. So here the work done will be integral f dx. This is a straightforward thing. So force is nothing but kx cube into dx. So W1 is integral kx cube dx. So this is going from x naught to 2x naught. This is 1 by 4 k 2x naught power 4 minus x naught power 4. That will be how much? 16 minus 1, 15 k by 4 k x power 4. What is W2? Same formula, kx cube dx. The only thing that will change is the limits. 2x naught to 3x naught. X cube dx integral is x power 4 by 4. So 1 by 4 k x power 4. 3x naught power 4 minus 2x naught power 4. That's 81 minus 16. That's 65. So W1 by W naught is 3 by 13. Easy. It's more of a work question. Clear with this? And in this case, if they ask you spring potential energy, it will be 1 by 4 k x power 4. So I didn't ask you that, but if at all they try to ask you this. So in this weird spring, the spring potential energy will be 1 by 4 k x power 4. So that formula of kx square is derived for a standard spring where f is equal to kx. Clear with this? Any doubts on this? Clear, na? Vedika? Advai? Aditi? Rudransh? Next thing. Great. So now we have an idea about energies and we have an idea about work and force. Now let's combine them. Work energy theorem. So what is work? Integral F bar dot R bar. And what is force? Force is nothing but mass into acceleration. And what's acceleration? M into V dV by dr. So you integrate with M into integral V dV. So if you integrate this from U to V, you will simply end up with half mv square minus half mu square. There, this is your first thing. So work done by all forces is half mu square minus half mu square. Change in kinetic energy. So if you take all the forces, then the total work done must be equal to change in kinetic energy. Now remember, we wrote one more formula before this, that is work done by internal conservative forces. And this is how they'll ask theoretical questions. They'll ask you what is work done by internal conservative force? Work done by all forces. Work done by internal conservative forces is negative of change in potential energy. So be careful, don't mix up the formulas. And the minus sign is important. I have seen most people forgetting the minus sign, and unfortunately, there are two options. Work done by internal conservative forces, change in potential energy, negative of change in potential energy. In a hurry, people take the change in potential energy and come, and you get a -1. If your cams are not on, I'll just start removing you from the classroom. So I won't repeat again. Please don't make it a habit. This is not right. After telling so many times you do this, it will be very, it feels like you just don't care. That's what I should assume. Clear with this? If it's camera, putting a camera is becoming a really problem, no issue, right? You can talk to Vimy ma'am. We will refund the fees. You can leave the classroom. There's no issue. Please find someone else. Next thing. Now, when you say work done by all forces, you can classify all these forces into work done by internal conservative forces. So you can split them into two categories. And you can just separate everything into work done by external forces. So in order to avoid confusion, to keep it simple, whenever it's internal conservative forces, at least in our portion, we have only spring forces. So all spring forces and gravitational forces and electrostatic forces. That's it. Generally, these are the only three forces we deal with. These things are internal conservative forces. Everything else is taken as external force. Friction, air resistance, or any force that you apply from outside. That means all forces can be classified into internal conservative forces and external forces. So then your formula becomes work done by external is equal to change in kinetic energy. But we already know work done by internal conservative forces is minus delta U. So we get work done by external forces is change in kinetic energy plus change in potential energy. So if you combine this, change in potential energy plus change in kinetic energy. So we call this potential energy plus kinetic energy as total mechanical energy. So we write work done by external forces is change in total mechanical energy. This is your third formula, everyone. There have been questions like this. What is work done by all forces? Change in kinetic energy. What is work done by internal conservative forces? Negative of potential energy. What is work done by external forces? Change in total mechanical energy. So these questions generally, right, they'll put it in a statement and they'll ask which of the following is right. This is actually your work energy theorem. So this can be also written as, now you can keep playing with this few models. So you can write this thing as E final, the total final energy, minus E initial energy. You can also write this thing as, a more intuitive way of writing is this. E final is E initial plus work done. Think of like this. You have 100 rupees, that is your initial energy. I gave you 50 rupees, that is your work done. So how much should you have? 100 plus 50, 150. Making sense? You can read it like that. So all the same thing, you're just playing around. This is your work energy theorem. Work done by external forces is change in total mechanical energy. If someone asks you what is work energy theorem, this is the thing. Work done by external forces change in total mechanical energy. Now here we have a special case of this. If work done by external forces is zero, means if external forces don't do any work, then we get E initial is equal to E final. This is your law of conservation of energy. So actually law of conservation of energy is a, what do you call it, a simpler form of work energy theorem. Work energy theorem is more powerful. So you can use this only when you're sure external forces don't do any work. This is our first conservation, everyone. In physics, we have three conservations primarily in mechanics: momentum, energy, and angular momentum. So energy is our first thing. This can be also written in another form. If work done by external is zero, then we get delta U plus delta KE is zero. So that means you can write delta KE is equal to minus delta U. This you must have studied in school. Gain in potential energy is equal to loss in kinetic energy. So all these are simply, different forms of work energy theorem. So loss in potential energy is gain in kinetic energy. There, have a look at this. Again, so in this whole story, in the whole story, right, these are the important ones. The definitions are important. Work done by all forces, work done by internal conservative forces, and work done by external forces, which is change in total energy. If work done by external is zero, then initial is equal to final. That's your conservation of energy. Any doubts on this? Clear with this? Great. Now, in this, there's one more variation. What if the observer is not in the inertial frame, but in a non-inertial frame? So if you're standing in a non-inertial frame, then you get a pseudo force also. Then your work energy theorem becomes like this. So work done by external force plus work done by pseudo force. You have to include the work done by pseudo force also. Will be equal to change in kinetic energy plus potential energy. It works. So if you include the work done by pseudo force, then your work energy theorem is valid. If you don't do that, you won't get the answers. That if you can ask, this is the final form of this. Even in a non-inertial frame, you can use work energy theorem if you include the pseudo force ka work done. Clear with this? So there, we learned how to find work. We figured out what are energies, and then we found a relation between them. So how do we solve problems? Clear so far? Anyone has any doubts? Utsa, clear with this? Ovia, got something? Anyone? Ovia, got something? Have a doubt. Pseudo force is not real. Huh. So the thing is that it is a mathematical correction. So when you're doing problems, you're introducing pseudo force, right? So see, it doesn't exist, but for problem solving, right, to use the Newton's laws of motions, we actually use pseudo force for the correction. So it starts behaving like a force which exists, but like I said, it doesn't exist, but mathematically it works out. Clear that? So we will see. Because if you don't put that, first of all, laws of motion won't work. Then all these things are wrong, no? Yeah, देखो, ये derivation में this F becomes what? This F becomes the external forces plus pseudo force, isn't it? If you're in a non-inertial frame. So that FDR becomes a pseudo force ka work done. Now, steps to solve. Utsa, I can't see you, Ray. Your camera is somewhere else. Rudransh, I can't see you also, but I think it's fine. Advait, please adjust your camera. Please make sure your faces are visible on the screen, everyone. So how do you solve problems? We have written something like this in NLM. So first thing, choose your system. And define your initial and final state. This is important. So whenever using conservations, always define what is your initial and what is your final state. I'll show you some examples. Second thing, choose your reference line. Calculate gravitational potential energy. Spring potential energy. Kinetic energy at initial and final state. Step 3, find work done by external forces. Step 4, use work energy theorem and solve. The idea is pretty simple. Let's see some things. Let's see some questions. You'll get the hang of it. There. So the basic theory is done. Now the main thing comes up. Let's start off with a question. Then let's try to see with the steps also how it works. Let's start with something easy. So let's say we have a surface like this. Smooth surface. This height here is 5 meters. This height here is 10 meters. This height here is 20 meters. And let's say this angle is 60 degrees. And you released a ball from here. So let's call this point A. This lowest point is B and this point is C. So what will happen? This ball will start rolling down the surface. And then it goes there and then it flies and falls on the ground. This is your range. And when it hits the ground, let's say it hits at an angle alpha. The ball rolls along ABC and falls on the ground at point D. Find the range and find alpha. So range is that horizontal distance on the ground, and alpha, without what angle does it hit the ground? Alpha is the angle made by the velocity vector when it hits the ground. Let's start with something simple. Can you find the velocity at point C? Start from there. Find the velocity of the ball when it is at point C. Let's start from there. And then from there, we'll take it up. Let's see, velocity you must have got. Okay, range. I thought range is bad. I hope you guys are not using u square sine 2 theta by g for range. You can't do that. It's thrown from a building. Okay, let's start with this thing. Listen carefully how to handle this. Let me show you one. So forget about this range and everything for now. Let's start with this point here. Step 1, choose your system and define your initial and final level. What is my system? The ball is a system. Define my initial and final state. This is my state 1. The point A. C is my state 2. That is where the ball flies off. What about B? I don't care. You are only interested in the initial and the final state. So when the ball reaches here, the ball will have a speed, let's say V. Initially, your speed is 0. Step 2, define your reference line. You can choose anything as your reference. I will choose the ground as reference. Then gravitational potential energy, mgh, which is mg20. Spring energy, 0. There is no spring, but I'll just write it for now. Kinetic energy, 0, because you're starting from rest. State 2, gravitational potential energy, mg10. You're at a height of 10 meters from the ground. Spring potential energy, there is no spring, so 0. Kinetic energy, half mv square. This is my second step. Step 3, find the work done by any forces. Now, when I say work done by external forces, remember, except gravity, spring, and electrostatic forces, every other force is external force. So, are there any external forces on the ball? There is mg, but that is internal conservative force. There is one more force on the ball, normal reaction. So, when you look at the ball here at any instant, there is a normal reaction. So, there is an external force. Getting it? But work done by normal force is 0 because it is always perpendicular to the displacement. That's why it is called normal. So even though there is a force, there is no work done. Work done by normal force is 0. Since N is perpendicular to displacement. This is important. You need to see whether there are forces or not. Is there any other force? Mg, normal reaction, that's it. There are only two forces. So you're done. So work done by external forces is zero. Since work done by external is zero, energy is conserved. Energy in state 1 is equal to energy in state 2. So initial energy mg20, final energy mg10 plus half mv square. I know, it's simple thing, but this is how you go with the steps. 100, this is v square by 2. So we get v is equal to 10 root 2 meters per second. Clear with this? I should have given maybe 45 degrees, I guess, but yeah. Any doubt still here? The speed part? Where did I miss something? mg20 200. 200 root 2, yeah. Is this clear, everyone?
So what are we taking as a system here?
Ball and the
So-
earth ka thing. So
Yeah, sir. So okay, so work extreme is my bad.
see, the moment you use the word potential energy, earth is included. Clear with this? Let's do for one more guy here. Huh? If you see, this ball also goes here and lands on the ground. So this is point D. So point D is my state 3. So I can conserve energy at point D also. Right?
सर टेक्निकली तो ग्रेविटेशनल फोर्स आपने बोला सेंट्रल फोर्स है तो उसका वर्क थोड़ा अलग रहेगा पर वी आर इग्नोरिंग दैट
Where, but that is taken care, na? We are taking earth to be flat, Ray. That's an approximation. So if you take the point D ka reference also, now at D, what is the gravitational potential energy? 0, because you're on the ground level. Spring energy, 0. Kinetic energy, half mv d square. So you can even conserve energy between state 1 and state 3. So you can conserve energy from anywhere to anywhere in this case. You will see why we need speed v. Half m v d square. So speed at point D is 20 meters per second. Is this clear, everyone? We are just finding speeds here. Any doubts on this page? You found the speed at point C when it is leaving the incline, and you found the speed when it is hitting the ground. Once you're done this, you are kind of done basically. You will just need to use the projectile motion. So we got a, basically the question has become like this. We got a building here of height 10 meters. And the particle is projected with speed Vc, which is 10 root 2. And what about this angle here? So if this is Vc, this is 60. This angle is actually 30. Look at that angle there. If we take this is 60 degrees, this is 60 degrees. That means with the horizontal, it is 30 degrees. So this being projected with 30 degrees. So be careful with that, it's not 60. And then it goes from here and falls on the ground. This though you know how to do, just regular kinematics. We can use Sy is equal to Uyt plus half Ayt square. Your Sy is minus 10, Uy is 10 root 2 sine 30. Numbers are bad. This will be half G is 10 t square. You'll solve this, you'll get t from here, and range will be horizontal velocity into time. You can leave it here, it's okay. And what about this angle alpha? When you hit the ground, you're hitting with the speed Vd. We know in a projectile, this is a pure kinematics question after this. We know u cos theta is equal to v cos alpha. So here u is 10 root 2 and theta is 30. V is 20, just now we calculated that, into cos alpha. There, so we get cos alpha will be, how much is that? Root 2 by 2, root 3 by 2, root 3 by 2, root 2. Check. Any doubts on this? First of all, see, at this point here, the work per energy is over. If you can find the speed at C, if you can find the speed at D, your job's done. Then it simply becomes a projectile equation. Any doubts on these steps? Shreyan, clear with this? Vanchika? Tanishka? Aditi? Any doubts on this? Devanshi? Clear with this? Great. Take a small break. Come back by 9:30. We'll continue from here. Any doubts so far? Chalo, come back in 5 minutes. Let's see one more. So we have a block of mass M here. It is connected over a pulley here. We have another block of mass M here, same mass. So initially the system is at rest. So let's call this thing as block A and block B. So let's say this point is P and this point is Q and this is 2 meters. If you guys remember, we did something like this in foundation. Find the distance traveled by B when the block A moves by P to Q. So initially this angle is 30 degrees. The ground is smooth, so there is no friction, nothing here. So if I leave it like this, do you think it will be at rest? The block will start sliding. The block will start sliding and the block will come somewhere here. Then the string becomes like this. This block also must have come down like this. This is how the picture will become. This angle becomes 60 degrees. All surfaces are smooth. So block A slides from P to Q 2 meters. Right? PQ is 2 meters. Starting from rest. Find the speed of the blocks when A reaches point Q. NLM and work per energy. Is the question clear? So we have block M and N, both are same masses, A and B. Initially, block A is at point B, released from rest. Because the ground is smooth, the block B will pull it down. So block M will slide on the horizontal floor and will reach point Q. In this process, the angle has become 30 degrees to 60 degrees. Clear with that? To find the speed of the blocks when the block A reaches point Q. Near area, that is wrong. Let's get this. Let's see how will you handle this. There are multiple aspects to this problem. And the first time you saw this problem was in basic maths foundation course. Maybe we did this thing. Yeah, the question. This was a question which was first class basic foundation. Find the distance moved by the 2 kg block when the 10 kg goes from A to B. Similar question. Let's try. I'll give 3-4 minutes. It's a good one. It's a tough one also. Anyone not clear with the question or the picture, please ask me. Let me start with this. In case you're confused how to start, let me ask you a simple question. When A goes from P to Q, what is the distance moved by B? Can start from there. Let's start from there. When this block A goes from P to Q 2 meters, how much will the block B come down? Start from there. Once you got how much block B comes down, then you can clearly see whatever potential energy B loses, that will be the gain in kinetic energy. Then we use work energy theorem. But let's start with that. When A goes from P to Q, how much will B come down? Any things? Did you guys figure out how much it will travel down? Let me help you with that. See. Look at this. So what is the distance moved by the block? If you take this point as A and this point as P, right? And finally, when the block comes somewhere here, so let's just call this point as A and A dash. Now, let me just take it as P is anyway given. Na? This was P, this was Q. Let's take this point as R. So what is the distance moved by the block? Again, for people who don't remember, listen to this thing. Imagine just, let's say this length is 10 meter, example, and this length is 6 meter. So my question is this, initially this rope ka length was 10 and this rope ka length was 6. So the question is, what happened to the difference? The difference in string must have gone somewhere. So that must have gone down from B, isn't it? Do you guys remember that logic now? So how much did B move actually? B didn't move 2 meters, everyone. The distance moved by B is the difference in length of the string from the block to the pulley. Basically the difference in the hypotenuse. Difference in length of the string from block to pulley. Which is PR minus QR. That is the distance moved with the block B. If you look at these angles here, this is 30 degrees. This is 60 degrees. I can just make a triangle. This is 30. This is 60. This is 120. And this is 30. It is actually an isosceles triangle. This is P, this is Q, and this is R. This is 2 meters. So this is also 2 meters. You can use sine rule. PR, the side by the opposite sine angle, 120, must be equal to PQ by sine 30. So we get PR is equal to 2 root 3. Therefore, distance moved by B will be 2 root 3 minus 2. This is the distance moved by the block. The block did not come down by 2 meters. All clear with this? This is the first part of the problem. When A goes from P to Q 2 meters, the block didn't travel 2 meters. It traveled 2 root 3 minus 2. Any doubts on this part? Second part. Now we can clearly see from here, there are no external force on the system. See, tension does not, the total work done by tension is 0, right? Tension is internal there. only mg is there. So there's no other force doing work. Since work done by external is 0, I can use this one. Loss in gravitational potential energy is equal to gain in kinetic energy. Now, this is where some people goof up. Let's see whether you did that goof up or not. Now, the only person who is losing potential energy here, A is going on the ground, so only B is losing potential energy. That will be mg h of B. Gain in kinetic energy, both A and B are gaining kinetic energy. And be careful, A and B ka speed is not same. That is a mistake people do. They think A and B because they have same speed. They don't have same speeds. Then what is the speed ka relation? Constraint equations. If you look at the A and B ka blocks, so let B go down with VB. This is your tension. This is your tension, and this is your VA. And this angle is 60 degrees at that instant when you're at Q. Power method, T VA cos 60 minus T VB is equal to 0. So VA by 2 is equal to VB. This is the relation between VA and VB. Hope you have taken this into account. A and B don't have same speeds. There, now you got everything ready. Did you see? We used constraints, we used the difference in length of the string. M is same everywhere, it will cancel out. This will be G and H is how much? 2 into root 3 minus 1. This will be half. VA square will be 2 VB whole square plus half VB square. This would be 20 root 3 minus 1, or you can leave it in terms of G. This would be 4 plus half pi by 2 VB square. That would be 5 4 so VB will be root over 8 into root 3 minus 1. Check. And VA will be half of this. So that would be, I can send 2 inside. It will be root over 2 into root 3 minus 1. Please check your answers.
Sir, VA is 2 into VB.
Yes, 2 into VB. Sahi hai.
4 into root 2 root 3 minus.
All right. ठीक है. Please check where it went wrong. If anyone got it, you got it, great. So this is the first thing. A and B don't travel same distances. A and B don't have same speeds. These are the two main things you should know. So once you got the lost in height, the lost in potential energy is gain in kinetic energy. All clear with this? There, NLM and work per energy. So that's what I keep saying. Everything you learned will keep popping up. Work per energy will be just a part of it. Any doubts? Anything that's not clear? Let's see one more. Let's see one more. We have a light rod. The one end is fixed. We have two particles here. It's like your paneer pieces on that barbecue nation. M and 2M. This is a light rod. This length is L and this length is L. Masses are M and 2M. So you released it from a horizontal position. So when you release it from horizontal position, what will happen? The rod will swing like a pendulum. This is how they swing like a pendulum. Gravity is there. A light rod with masses M and 2M, as shown, is released from a horizontal position. This is 90 degrees. Circular motion and work per energy. Find the speed of the particles and the tension in the rod at the lowest position. Find the speed and the tension in the rod at the lowest position.
So the tension in which part?
Find both now then. When you think there are multiple, then you find everything. Is the picture clear, everyone? Rod is light. Rod does not have any mass of its own. So one end is fixed and you're releasing it from a horizontal position. So it is swinging. To find the speed of the particles and the tension in the rod. So each section will have different tension. How do you know that? We have done a problem like that in circular motion. Remember this question? If you rotate a rod like this, each section will have different tensions. There is a question like that in circular motion. Let's get this. Let's see what you will do here. Anyone not clear with the picture, didn't understand the picture, please ask. Right, Siddesh. मेरे आ गया इतना अच्छा आंसर नहीं आएगा. Let's see the first part. Let's find the speed, okay? I hope you guys didn't goof up this. If you had goofed up, how many of you realize that both the balls will have different speeds? That is the important thing. Both the balls won't have same speed. Think about it. When the ball is at this position here, the rod will have same omega, na? The rod will have same omega. So if you look at the speed, actually, this point is going with L omega. This is going with 2L omega. Look at your fan. The tip of the fan is going faster than the middle of the fan, isn't it? The particles are not going with the same speed. The 2m ka ball is going with double the speed. This is the first thing that you need to understand. Both of them won't have same speeds. If you have taken same speed for both of them, the whole thing will go for a toss. So this is the first thing you need to realize. At the lowest position, both the balls will have same omega, but not same speed. Now start from there. Now then use law of conservation of energy. So let's see the picture, how it looks. This was M. This was 2M. So when this guy was swinging, so this will go in a circle of radius L. This will go in a circle of radius 2L. So at the lowest position, if you see, this will have speed V, let's say L omega. This will have speed V, 2V, which is 2L omega. So remember that the rods will have same omega. They don't have same speed. Same angular velocity. And we know V is equal to R omega. So the farther the particle, the faster it goes. That is the first thing you need to realize. Second thing, how much did this particle fall? This particle fell a distance of L. How much this thing fell? This thing fell a distance of 2L. Both the particles didn't go down by the same distance also. Since work done by external force is zero, there is no external force, tension is internal here. Loss in potential energy is equal to gain in kinetic energy. So both the particles are losing potential energy. How much? M is losing mgl and 2m is losing 2mg 2l. And what is the kinetic energy? M ka velocity is v square. 2m ka velocity is 2v whole square. So be careful, their speeds are not same. And then you're done. So this is 5 mgl. This would be, how much is this? 9 by 2 mv square. So we get v is equal to root over 10 gl by 9. This is the speed of that Eka ball. This is the speed of Vm. The speed of 2m will be double of this. This is a proper mains level question. Is the question clear, everyone? So see where it went wrong. I think most common mistake, people think both the speeds are same and then the whole thing goes for a toss. Can you go ahead, find the tension in the string now? Find the tension in the rod. That's the next part. I think looks like speed, most of you got it. Siddesh, right, that is right. Yeah, we have tension ka one answer, I guess. You're right. Try it, Shaurya. Try others. Get the tension in the thing. How do you find tension? Loss of motion, everyone. Draw your FBD. Simple thing, see, the moment I ask you find the force, the only way you can get forces is by drawing a free body diagram. Get this? I'll give you another minute or two. Right, Anvita. You got one. Now remember, each section of the rod will have different tension. So be careful with that. Try, everyone. Tanishka, solve. Everyone else, solve. You guys are not typing answers. You should type your answers. Don't keep waiting for me to write and then just copying. That won't help you guys. Everyone should try. It's okay if you don't get it. Samyak, that is wrong. Try. That you have to solve a bit. Don't forget the centrifugal forces. Since they're going in a circle, you have to include the centrifugal force also. And there's an mg also. And on that particle m, there are two tensions, one up and one down. So I hope you're drawing the FBD right. Let's see the free body diagram. So at the lowest position, this is M. What are the forces? Tension T1, your own weight mg, the tension T2. You are going in a circle. So I can use centripetal acceleration or centrifugal force. This thing will be T2. This thing will be 2 mg. This you are going in a circle. So here there'll be a centrifugal force, which is mv square by L, and this centrifugal force will be 2m 2v whole square by 2L. Hope you have written the terms properly. mv square by L, m is the mass, v is the velocity, and L is the radius. So for this guy, it is T1 is T2 plus mg plus mv square by L. And for T2, it is 2mg plus 4mv square by L. You know the values for v ka value, you can substitute here. How much is v square? 10gL by 9. That would be 10g by 9. That would be 18 plus 40, 58 mg by 9. So T1 will be 58 mg by 9 plus mg, and mv square by L will be another 10 mg by 9. That will be 68 plus 9, 77 mg by 9. Check your answers, everyone. Check karo, Arya, see where it went wrong. How did you get 59 Rovia? See where it went wrong, everyone. Did you guys forget some particular force, or did you do a calculation mistake? Clear with this? Got the steps now? Just be careful with the calculations. Numbers are not that great. Rest of you all got this thing, what we did? So the main thing is to realize they don't have same speeds, and then it is a circular motion there. Any doubts on this? Clear, na, Sudiksha? Devanshi? Clear? Advait? Aditi? Tanishka? Let's see one more. So we have a shape like this. This is the flat surface, which is rough. Friction and work per energy. U is 0.2. So these curvy parts are smooth. This is again another standard question at a mains level. You took a block here of mass m and released it from here. This height is 10 meters. So this region A to B is a flat rough surface. So when you release this block from rest, this will start sliding. So how will this block go? It will slide here. It will slide on the rough part, slow down, slow down, slow down, but it won't stop. It will go on this side. It will go lesser height. Then it will again come back, slide, 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 will go here. Then again it will go, slide, 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 go here. And then eventually it will stop somewhere. Find the position where the block stops. This AB ka length is 10 meters. The height you released is also, let's change this number. Let's make this thing like, and let it be 10 meters only, big deal. Solve. Find the position where the block stops. It will stop somewhere on AB. So exam your answers will be like this: 2 meters from A, 3 meters from B. It will be like that. Okay, it's stopping at B only. Yeah. Let's change the number. No? I don't want it to stop at B. Let's make it 7.5 meters.
Sir, why?
I don't want it to stop somewhere in the middle. कर मुझे लग ही रहा था वो 10 मीटर कुछ तो गड़बड़ होगा. Had a feeling, but I didn't think it will go and stop at B only. Take it 7.5 meters. Height is 7.5. Let's see how will you handle this. Now energy is not conserved because friction will dissipate energy. There you can see how I'm asking questions, right? Kinematics ka work per energy, NLM work per energy, circular motion work per energy. So I'm trying to show you what you did before. It will be the same stuff, but you're adding little work per energy somewhere in the middle of the problem. No, Siddesh, I didn't ask you that. I asked you where will it stop. That looks right somewhere. Let's see. Near area.
Okay, sir, I'm very sorry, sir. I took the like that length of
करो. Do it again.
S5
करो ना. अब इतना explain करने के टाइम में तुझे आज आंसर भी आ जाएगा. Get it done. Others, any other answer? Everyone else. Some of you are not typing anything. I want you to try. It's okay if you don't get it, but please put some effort. Siddesh, what do I understand from the 2.5 from what? You're supposed to tell me that. You can't ask me. So let's see. Yeah, I think now you got it. Ishman, that is wrong. Aditi, you got, but that's not what I asked you. Shaurya, that is wrong. Right, Arya, you got it. Let's see. First thing. Now ask yourself, when look at this block here, when this thing starts sliding left and right, eventually it will stop. So if you look at work done by friction, that will be minus mu mg because the friction and the displacement will be in the opposite direction into S. So what is this S here? S is the distance traveled on the rough surface. It's not the total distance because the friction will act only on the rough surface. The S also must be distance traveled on the rough surface. Okay. Now, this was your track. This was A and this was B. Step 1, choose your system and define your state. Block is my system and I'm defining my state. So this is my state 1. The block will stop somewhere in the middle. I don't know where. That is my state 2. Define your reference level and get the energies. I will take the ground as a reference line. So this potential energy will be mgh. Kinetic energy 0. Ground level potential energy is 0. I took ground as a reference line. Kinetic energy is also 0. Is there work done by external forces? Yes, friction is doing work. So work energy theorem, work done by external force is change in potential energy plus change in kinetic energy. Or you can simply write E final minus E initial. So work done by external forces is mu mg into S. E final is 0. E initial is mgh. From here I got S is equal to h by mu. H is 7.5 and mu is 0.2. This comes out to be 37.5 meters. So what did I get exactly? I got the total distance traveled on the rough surface. So when you started from A, you went from A to B this side, you covered 10 meters. then you went up, then you came back again you covered 10 meters, then again you went 10 meters, so it actually made 3 rounds, 30 meters, and then while coming back it traveled only 7.5 and stopped. Are you getting how to interpret this situation? So you basically travel 3 times front and back, once A to B, B to A to B, and then you travel 7.5 and stopped. So the answer is 2.5 meters from A or 7.5 meters from B. Both are right. From the options, you can mark one. Are you clear how to interpret these questions? Any doubts on this? Most of you got the 37.5. I think after that, you didn't understand how to proceed. So the 37.5 is the total distance traveled on the rough surface. All clear with this? Any doubts on this? Let's see one more. Let's see one more. This is fixed. We have a pendulum here of mass m. It's a string, length L, light string. Released from the horizontal position. Let's say this angle is theta. So basically this thing is going in a circle like this. A pendulum is released from the horizontal position. String is tight. So this will start swinging. First question, find the speed. Find A centripetal. Find A tangential. Find tension in the string when it rotates angle theta. Meaning when it has swung by an angle, when it has swung by an angle theta. Then the pendulum rotates by theta. Basically, at this position, I want you to find the speed, I want you to find the tension, I want to find A centripetal and A tangential. Find theta when the net acceleration becomes horizontal. Let's get this too. There. I mixed up circular motion, NLM, and work per energy. So you left the pendulum from a horizontal position, it starts swinging. So when it has covered an angle theta, find the speed, centripetal acceleration, tangential acceleration, and tension. And find the position where the net acceleration becomes horizontal. Let's see how you interpret that. You know what is a net acceleration? It is a resultant of A centripetal and A tangential. So that net acceleration should be horizontal. Speed is easier. Get the rest. Yeah, speed is right, Samyak. Right area. Centripetal. हाँ अभी सब आ जाएगा एक के बाद आके. Yeah, right, Shaurya. The speed part is easy. Let's go, everyone. Try. Loss in potential changes, gain in kinetic energy. Just give it a try. It's like most of you got the speed part right. If you got the speed, you'll get centripetal acceleration. Tangential also you'll get. Yeah, looks like most of you are getting the first part. Get me the answer for the second part. First one, I think most of you got it. Find the angle when the net acceleration is horizontal. Let's get that. Others, please continue trying the first part. I'll give you another minute. Then I'll show you the first part. People got the second part also. Tension is right. I think who got the second part? Someone got. Centripetal is 2G. Okay, let's see the first part, everyone. So if you look at this pendulum here, this is fallen by this distance here. So if this is L, this perpendicular distance will be L sine theta. So this pendulum has fallen a vertical distance of L sine theta. There are no external forces by the system. Tension is there, but it is always perpendicular. Gravity is internal, so that's it. There is no other force. So loss in potential energy, mg L sine theta, that is the height lost by the ball, must be equal to half mv square. That was straightforward. So v is equal to root over 2g L sine theta. What is a centripetal? V square by r. That would be 2g sine theta. Next thing, you want a tangential. So draw the FBD. What are the forces acting on this? Tension. And you have mg. Remember, this is theta, so this is 90 minus theta. This is your mg. So mg ka components will be, this will be mg cos 90 minus theta. So this is mg sine theta. And this is mg cos theta. That's it. There are only two forces, tension and mg. Now, since you're going in a circle, I'm doing in the ground frame. There will be a centripetal acceleration and there will be a tangential acceleration. Then I can write tension minus mg sine theta. So this is your net centripetal force. Tension minus mg sine theta is equal to mass into a centripetal. So we get tension is equal to 3 mg sine theta. And what about in the tangential direction? Mg sine cos theta is providing your a tangential, which is m into a tangential. So a tangential is g cos theta. Check. Right, Anvita. Right, Shaurya. नहीं रहा है, you will not get a good angle. कुछ तो हो गया तुझे. You're doing all calculation mistakes. See where it went wrong. Now, how do you find the angle where the acceleration becomes horizontal? Now look at this pendulum here. So this pendulum has two acceleration components. One is your a tangential, that is this way. One is your a centripetal. And I'm saying the net acceleration must become horizontal. So if this angle is theta, this is theta, and this is 90 minus theta. Now, since the net acceleration is horizontal, if you resolve this into components, a centripetal sine theta must be cancelling out a tangential cos theta. Then in that case, a net will be in this direction. Right? Since a net is horizontal, so a centripetal sine theta is a tangential cos theta. A centripetal is how much? 2g sine theta. A tangential is g cos theta. So we get tan square theta is equal to half. Tan theta is equal to 1 by root 2. That's your answer. Any doubts on this? Yeah, you can get sine theta also from here, but there. All clear the steps, everyone? Yeah, right, Utsa, you got it. Most of you got it. There, that is how they'll frame questions on this. Clear? Let's see one more. Let's do an easy one. We have a block of mass m here. There is a platform here connected to a spring. This is K, initially in natural length. And the block is released from height h. Find the maximum compression in the spring. Gravity is there. Let's finish off. Last one for the day. I know you guys are feeling bad. I didn't bring springs so far. Springs are also there. That might be right idea. देखना पड़ेगा. Most common mistake, what people think. They think mgh is equal to half kx square. Now, again, what do I keep saying? Choose your system and draw your initial and final state. Now listen to this. This was your initial state, state 1. Now, as the block falls, what happens to the spring? This is the scenario, everyone. So the block will hit this surface. Remember, the block will have some speed. How much? We don't know yet. And then it won't stop there. The block will keep going down. Eventually, the block will stop somewhere here. This is my state 2. So if you see from natural length here, let's say this thing has gone down by x. You can choose anything as reference. I'll choose this as a reference. So this is state 1, this is state 2. Gravitational potential energy, mgh. Initially, you're releasing from rest. Spring potential energy is 0 because spring is in natural length. Kinetic energy is 0 because you're starting from rest. State 2. Gravitational potential energy, your distance x below the reference line, minus mgx. Spring potential energy, half kx square because the spring got compressed by x. Kinetic energy, it comes to rest. Why it should come to rest? Think about it. If it doesn't come to rest, won't it just keep going down further and further? So when the spring is maximum compressed, the block comes to rest. Because if it doesn't come to rest, the block will still keep pushing the spring. So that is the thing you should realize, that maximum compression, block comes to rest momentarily. Next moment, it will get pushed out again. Next moment, the block will get pushed again. Again, it will start flying up. And this will just keep on going forever. What are the forces acting on the block? Mg, that is okay, internal. Spring, that is also internal. See, the moment you use the word gravitational potential energy, spring potential energy, they're taken care of. Any other force? There is no other force. Since work done by external is 0, energy is conserved. You get a bad quadratic. Energy in state 1 is equal to energy in state 2. So this would be mgh is equal to minus mgx plus half kx square. Quadratic equation. You'll take the positive root. So half kx square minus mgx minus mgh is equal to 0. So this would be x is equal to mg plus root over b square m square g square 4mgh. That will be 2mgh by k. You can leave it like this. Yeah. Clear with this? Now, there's a much faster way to do, right now, since we are starting, right, I'm showing you each and every step. If this comes in the exam, doing like this is a waste of time. What I would do is this. Finally, the block will come here. Itna to realize karna important, a diagram. So let's say this thing has gone X. So can I say directly like this? All the potential energy from H plus X has gone into the spring. Initially, block is at rest. Finally, the block is at rest. So all the gravitational potential energy, mg H plus X, must have gone into the spring. So half kx square. There, I'll just add one step and finish it off. At the end of the day, you'll get the same thing. But there, I'm just trying to show you more systematically. It's better you do it a little systematically in the beginning, and once you get used to it, then you can start skipping steps. So here you will write loss in gravitational potential energy is gain in spring potential energy. You're getting it? Because your initial and final velocity is 0. All the energy must have gone somewhere. That must have gone into the spring. All clear with this? So if you can do that, that will be great. See, but I have to show you detailedly what is happening. But exam mein to writing this will take a lot of time. It's a waste of time. I don't do this in the exam. When you're learning, it is better you do it systematically. How? Yeah.
Sir, in the x equation you got, why have you divided k? Like,
वो है ना minus b plus or minus root over b square minus 4ac by 2a. A is half k ना.
but 4ac should be equal to 2mgk.
Uh, 2mgh k na. I wrote wrong. Clear with this? That's few problems there. So next class when you catch, we'll continue from here. We will do even more tougher ones and little more different